Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about how to perform principal component analysis using StatCraft. Even before I proceed to demonstrate how to perform the principal component analysis using StatCraft, may I request you to subscribe to my channel, also like and share my videos. To begin with, what exactly is principal component analysis method? Firstly, principal component analysis is an unsupervised learning technique. I repeat, this is an unsupervised learning technique, which means that we don't have a dependent variable here. The second point here is that PCA is a dimension reduction method. It is popularly used to reduce the dimensionality of a very large data set. As you can see in the screen here, I have got a data set. I will be using this particular data set to extract principal components from the data set. This is college level data. This has infrastructure information for different states in India. So the first variable is state, then you have district, then you have different infrastructure provided by the university to its students. A typical university may have playground, you can have auditorium, theater, library, laboratory, conference hall. Like this, you have 21 different infrastructure facilities. We can have a cafeteria, guest house, separate room for boys and girls. You can have solar power generation, so on and so forth. These are the 21 variables which I will be using to execute PCA. And we'll also be extracting 4 important components. The main agenda behind today's presentation would be to tell you about the Scree plot. Secondly, to talk about the Varimax rotation. And thirdly, I'll also be talking about the path diagram in StatCraft. Let me minimize the Excel sheet. What you're seeing now is StatCraft. This is a Make in India initiative. This is a very popular and a widely used tool, both in academics as well as in the government sector. It has a very friendly spreadsheet-like view. I've already loaded the data set into StatCraft. All that I need to do is go ahead and execute the principal component analysis method. To perform the principal component analysis method, you can click on the analysis tab, which is present at the top left-hand side corner. The menu appears here. You can scroll down. As you scroll down, you can see the option which is called as dimensionalities. You can go ahead and click on the option dimensionalities. Once you click on the option dimensionalities, what you see is 3 different options. The first option that you're able to see is what is called as factor. The second option here is PCA, and the third option here is LDA, or linear discriminant analysis. I will choose the second item here called as PCA, or principal component analysis. The moment I choose the PCA, you can see here there's a new dialog box which pops up. As you can see here, all the variables that are present in my data set are displayed in the canvas to the left-hand side. I need to push these variables into the items which are called as variables. Let me go ahead and choose these 21 variables. Playground, auditorium, theater, library, laboratory. Let me scroll down. You can see variables like conference hall, health center, gymnasium, indoor stadium, common room. You have the cafeteria, then the guest house. Let me scroll down further. You can see solar power generation, connectivity facility, campus friendly, grievance redressal mechanism. You have the vigilance cell as well as the opportunity cell. So these are the 21 variables that will be used for principal component analysis. You can see here, StatCraft is asking me the number of factors to extract. Now, to kickstart this process, I'm going to say 4 factors. You can choose any number. This is an experimental process, and therefore you can choose any number to begin with. After specifying the number of factors, the next thing that I'll be doing is heading over to the top section. You can see an option here which is called as rotation. There are 2 types of rotation. One is called as orthogonal rotation. The second one is called as oblique transformation. Orthogonal rotation has different examples like varimax rotation, quantimax. You can also use varimin or equal max rotation. What exactly do we mean by orthogonal rotation? Orthogonal rotation ensures that we get principal components which are completely independent of each other. It will ensure uncorrelated principal components. On the other hand, if you want to make sure that the components have some degree of correlation, instead of choosing the orthogonal rotation, you can choose any of the examples of oblique transformation like Promax or Oblimin or Simplimax. There are a whole lot of options. I will not be going into each of this option. For all practical purposes, the popular method, namely varimax rotation under the orthogonal type, is what I will choose. Remember, rotation helps us interpret the components better. Without rotation, it is very, very difficult to interpret the meaning of the components. Once you choose the rotation option, the next item here is options. Let me go ahead and choose options here. You again have a lot of options to choose from. I'll choose the eigenvalue. This is very, very important because this option of eigenvalue tells me what is the exact number of components that I need to extract. Should I choose 3 components, 4 components, or any other number? Eigenvalue is a popular and a widely accepted method which tells me what is the optimal number of components to extract from. The next option here is plot. There are different plots here. I'll choose the correlation plot. I'll also go ahead and choose what is called as the path diagram. And finally, I'll choose the Scree plot. These are the 3 options that I will be choosing from. The last item here is save. If you want to save the principal component scores for any advanced analysis, you can go ahead and choose the principal component scores as well. What this does is it will create 4 additional variables in the data set. I repeat, principal components. If you choose this particular option, it will go ahead and create 4 new variables in the data set. With these selections, let me reiterate the selections. I have chosen 21 variables and I have guessed that 4 would be the number of factors. It could be 3 or 5. This is an experimental process. So we need to experiment with the number. Next, I've gone to rotation and you can choose varimax rotation. In options, I've chosen eigenvalues. When it comes to plot, I'm interested in seeing a correlation plot, a path diagram, and a Scree plot. Finally, I have asked StatCraft to save the principal component scores in my data set. After the selection, you're ready to hit the OK button. StatCraft takes a couple of moments to execute the principal component analysis method. This is the output window that you are seeing. Yes, StatCraft prints a lot of output and a lot of interesting details. We don't need to look at all the output. I want to keep it very simple and focused for this particular video. So let me draw your attention to only the necessary tables here. I'm going to ignore unimportant things as far as this particular video is concerned. This is important. So as you can see here, this is what is called as the eigenvalue table. I repeat, this is what is called as the eigenvalue table. What is the optimal number of components that you need to extract? This is the most important question. What is the optimal number of components? That is the first question that we are trying to address. The second question that we are trying to address is, what do these components represent? To answer the first question as to what is the ideal or optimum number of components, there is a statistician called as Kaizer. Kaizer, way back in 1960, proposed a criteria which is called as the Kaizer criteria. This is the best known and most utilized method. What Kaizer said is eigenvalue greater than 1 should be retained for interpretation. I repeat, if a particular component has an eigenvalue greater than 1, extract it. If a particular component has an eigenvalue less than 1, ignore it. You see two columns. This is the first component, second component, third component, and the fourth component. As per the Kaizer criteria, or it's also referred to as the K1 criteria. K for Kaizer and 1 is the eigenvalue greater than 1 criteria. The first component in this data set has an eigenvalue of 5.8, which is clearly greater than 1. So the first component qualifies. The second component has an eigenvalue of 1.65, which is again bigger than 1, and therefore the second component also qualifies. The third component has an eigenvalue of 1.42, which is again greater than 1. So the third component also qualifies. The fourth component has an eigenvalue of 1.1, which is greater than 1. Therefore, the fourth component also qualifies. Let me draw your attention to the fifth component. Here, the eigenvalue is 0.8, which is clearly less than 1. And therefore, the fifth component does not qualify. We have to draw a line here and say that the first four components qualify, whereas the remaining components, you can see here, the sixth component, seventh component, and eighth component, in fact, all the successive components have an eigenvalue of 0 point something. It's either 0.87 or 0.84 or 0.79 or 0.76. Whatever be that number, it is clearly less than 1. Since only the first four components have an eigenvalue bigger than 1, the optimal number of components that we need to extract would be 4. This settles the first question. Remember, the first question was how many components should we extract? The K1 method says that extract those many components as when the eigenvalue is bigger than 1, right? So eigenvalue method can be used. Let me draw your attention to an academic discussion here. There is one big criticism of the Kaizer criteria. And that criticism has been made in a lot of literature. According to Cattle, in the year 1966, he says that this is the least accurate method. He says K1 method is the least accurate method, and hence what he suggests is combining this criteria with other methods like examining the Scree plot is advisable. So don't just look at the eigenvalue. Also, you can supplement the eigenvalue method with what is called as the Cattle's Scree plot method. Look at both of these methods, and once you look at both of these methods, then you can decide what is the optimal number of factors. So I've looked at the eigenvalue method. Let me supplement this with another useful method, which is called as the Cattle's Scree plot. There are a lot of insights here. Let me draw your attention to the Scree plot. You can see here the Scree plot. In the y-axis, what you're able to see is the eigenvalue. You can see the eigenvalue in the y-axis. And in the x-axis, what you're able to see is the different components. We have 21 components. Against each of these 21 components, the eigenvalue is marked. You can see two lines here. One line here, you can see the legend here. The first line here represents the principal components. And the second one here, which is the dotted line, represents factor analysis. I will only be looking at the PC line. You can see here the first principal component. It has an eigenvalue close to 6, which is good. It qualifies for extraction. The second one, you can see here the eigenvalue drops here. There's a sharp dip here. The second one has an eigenvalue which is far less than the first one. However, the eigenvalue is still greater than 1. Let me look at the eigenvalue for the third and the fourth one. It is greater than 1. What Cattle's Scree plot suggests is that it helps us decide the optimal number of factors. Scree plot involves the visual exploration of the graphical representation of the eigenvalues. He suggests inspecting the nature of the bend. Very important. He says, look at the nature of the bend or the elbow. Sometimes we also refer to this as the inflection point, where the slope of the curve flattens. You can see here, as far as I can make out, the first inflection point happens here, but this line is not flattening. There's a dip here, and after this, the line more or less flattens. Secondly, you can see here in the y-axis, this is the cutoff that we have an eigenvalue greater than 1. There are 4 points. One, this is the first one, second, third, and if you go and look up, there is the fourth point there. So there are 4 points above the eigenvalue 1, which again strengthens our belief that there are 4 components which you need to extract. Again, there is no method which is completely free from criticism. What is the biggest criticism of the Cattle's Scree plot? The advantage here, no doubt, is that it's very, very easy, and visual inspection itself tells us what is the optimal number of factors. However, the biggest criticism is that there could be multiple inflection points. As you can see here, this could be the first inflection point, this could be the second, and perhaps this could be the third inflection point. Which inflection point would you choose? This is very, very subjective. This is very, very subjective, and hence, because of a lack of objective definition of the cut point by Cattle's approach, many times people again do not completely rely on the Scree plot. So we have looked at 2 different criteria. One is Kaizer's criteria. The second one is Cattle's criteria. There are umpteen number of other methods which will allow you to decide on the optimal number of components. However, for all practical purposes, I will just be looking at these 2 methods, that is the Scree plot as well as the eigenvalue. Remember, if the Scree plot, in the Scree plot, you have to look at the inflection point or the elbow of the graph, where the lines sort of flattens, it's almost parallel to the x-axis. That is the point that you need to look at, and above, how many ever dots are there, those many components you need to extract. We have already discussed the criticism of the Scree plot, which means there's a lot of subjectivity. There is no objective definition of the cutoff point here. Now, the next interesting thing that we will be doing is to look at what is called as, this is not the graph which I'm looking at. I'm looking at another graph which is called as the path diagram. That's very, very interesting. You can see here, this is the path diagram. Let me go ahead and zoom this for better visibility. You can see here, this is the path diagram. You can see the original variables here, like health center. You have one of the variables here, which is basically health center. The second variable is guest house, indoor stadium, theater, gymnasium, auditorium, solar, power generation. So these 7 original variables are loaded with RC3. RC3 refers to rotated component number 3. So the third component mainly is loaded with health center, guest house, indoor stadium, so on and so forth. The numbers that you see on the line represent the loading. They represent the loading, which means basically that health center has a loading of 0.7 on the rotated component number 3. Guest house has a loading of 0.6. Similarly, indoor stadium also has a loading of 0.6. Since these variables have a high loading on RC3 or the rotated component number 3, you can say that rotated component number 3 mainly represents health center, guest house, and indoor stadium. Let me scroll further down. You can take a look at RC1 or rotated component number 1. Here you have some of the variables like grievance redressal mechanism. Look at the value of loading 0.8. It is very, very high. Next is opportunity cell, and you have vigilance cell. Also, you have campus friendly. So these variables like grievance redressal mechanism, opportunity cell, vigilance cell, all these variables are heavily loaded with rotated component number 1. So you can say that rotated component number 1 mainly represents these 3 variables. Let me scroll down further. You can take a look at rotated component number 2. Which are the variables which are loaded with rotated component number 2? Common room, library, computer center, separate room for girls, playground, conference hall, and laboratory facility. These are some of the variables which are loaded with rotated component 2. However, I mainly see 0.7 as a very high number, and therefore common room, library, and to some extent, even to a large extent, even computer center, these are the 3 variables which seem to be loaded with rotated component number 2. Finally, you have the internet facility, that is connectivity, NKN, and connectivity, NMEICT. These are the 2 variables related to connectivity which have a high loading with rotated component 4. So connectivity, internet connectivity facility is loaded with rotated component number 4. Variables like, let me scroll up, common room, library, computer center are loaded with rotated component number 2. If I scroll further up, grievance redressal mechanism, opportunity cell, and vigilance cell, these 3 variables are rotated with rotated component number 1. And finally, what you see is health center, guest house facility, and my apologies, indoor stadium are loaded with rotated component number 3. So this is how a path diagram, what you're seeing in front of your screen, is called as a path diagram. This path diagram is very, very useful to understand the underlying structure in the data set. You will be able to map which original variables are loaded with which component. Let me move to the last of the tables here. We have looked at the Scree plot. I have the last of the tables, which is the correlation table. You can see it through a correlation plot here. You can see here there are 4 components: rotated component 1, rotated component 2, and rotated component 4. And if I were to scroll up, you can see rotated component number 3. You can see along the diagonal, it says 1 because we are looking at the correlation of each component with itself. So a variable will be highly correlated with itself. So the correlation is a perfect correlation of 1. We don't need to look at the diagonal elements. May I draw your attention to the upper triangle values? The upper triangle values, in fact, is a mirror image of the lower triangular values. Let me draw your attention to some of the important numbers here. You can see here, what is the correlation value between rotated component 1 and rotated component 3? It is 0. What is the correlation between rotated component 2 and rotated component 3? Again, it is 0. The correlation between rotated component 2 and 1 is 0. In fact, every number here is 0, which means that there is 0 correlation between each of these rotated components. Every component has a 0 correlation with every other component. So what do we infer from this? We infer that these components are completely uncorrelated. They are completely independent of each other. Now you may ask me, what is the benefit of having independent components? Now this is very, very useful because the condition of independence becomes very, very important if you're doing some advanced analysis like linear regression. Remember, when you are doing linear regression, one of the assumptions is that the independent variables must be uncorrelated. else it leads to the problem of multicollinearity. Multicollinearity happens when the independent variables have a high correlation. So one of the methods to remove the correlation from the independent variables is PCA. So you do not have to stop here. PCA has a great benefit in the sense that it produces rotated components which can be used as independent variables in regression analysis if you want to go ahead and perform some advanced analysis. You might ask me this question: how do I extract the component scores and perform advanced analysis? Now, to do this, I'm going to click on the view button. Here, I'm going to choose the data option. This is my original data set. You can see here state, district, and the different infrastructure facilities. Let me scroll to the extreme right side. What do you see here? Because I had saved the component scores, you can see here these are the 4 new variables that PCA has created. This is RC3, or this is the variable corresponding to rotated component number 3. You have the second variable, namely rotated component 1. Then you have rotated component number 2 and rotated component number 4. These 4 variables are completely independent of each other. They have a zero correlation, and therefore, instead of using the 21 original variables of infrastructure present in the data set, 21 is massive. We've successfully reduced from 21 to a lower dimension of only 4 variables. Studying 4 variables is a lot easier than taking 21 variables. Second advantage here is that these 4 variables are completely uncorrelated, and therefore you can use them as independent variables. With this, I have come to the end of today's video. In today's video, we have seen what exactly is PCA, what are the benefits of using PCA. We took some time to understand Scree Plot. We understood the criticisms behind Scree Plot. We also looked at the K1 criteria, or the Kaizer criteria. Nextly, we looked at how to generate principal component scores. I thank you very much for watching this particular video. I request you to subscribe to my channel, also like and share my videos. Thank you very much for watching this video. Have a great day ahead.